Good morning to one and all. This is DLN Sai Jishnu. I'm from CSD Data Science, CSC Data Science B section. Today I'm gonna discuss about concept video of applied physics. The concept is spectral distribution in blackbody radiation. These are the contents that we are gonna discuss in this PPT: spectral radiation in blackbody radiation. First, introduction is also known as similar to motivation. Definition of black body radiation loss, applications of black body, conclusion, summary. First, motivation. Black body is important in thermal radiation theory and practice. The ideal black body notion is important in studying thermal radiation and electromagnetic radiation transfer in all wavelength bands. The blackbody is used as a standard with which the absorption of real bodies is compared. This is the in basic introduction of blackbody radiation. Definition of blackbody radiation. A blackbody is an ideal body which allows the whole of the incident radiation to pass into itself without reflecting the energy and absorbs within itself this whole instant radiation in brackets without passing on the energy. This property is valid for radiation corresponding to all wavelength and to all angles of incidence. Therefore, the black body is an ideal absorber of incident radiation. This is known as the definition of the black body. The right side picture shows that how it works. It comes from an incident ray, then it reflects of the sir in the reflexes of the whole surface of the body. This is known as black body radiation. Without reflecting the energy and absorbed within the whole instant radiation. This process or property is known as blackbody radiation. The picture is taken from the University of Oregon website. Uh, we discussed about the introduction, definition of blackbody. Now we are gonna discuss about blackbody radiation loss. The Rayleigh-Jeans law. First one, the Rayleigh-Jeans law. It agrees with experimental measurements for long wavelength. It predicts an energy output that diverges towards infinity as wavelength grows smaller. The failure has become known as the ultraviolet catastrophe. In formula based I comma lambda comma t is equals to 2 pi c k t lambda per 4. This is the first law of blackbody radiation. The Rayleigh-Jeans law. It is known as the Rayleigh-Jeans law. The right side one is the graph between intensity and wavelength. The blue line shows the Rayleigh Jeans law first, starting from low to high. In this slide, we are gonna discuss about blackbody radiation law 2, Planck's law. We have two forms as a function of wavelength. First one, I into lambda comma t is equals to 2 he 2 lambda per phi into 1 by h e r e power rt. This is the first equation of a Planck's law. And as a function of frequency, I into Vt is equals to 2hv power whole power 3 by speed of light whole square by 1 hv into e power kT. This is the second equation. The Planck law gives a distribution that peaks at certain wavelength. The peak shifts to shorter wavelength for higher temperatures. And the area under the curve grows rapidly with increasing temperature. This is known as Planck's law. This is the another law, beam displacement law. Delta max is equals to B by T. It tells us we heat an object up, its color changes from red to orange to white hot. You can use this to calculate the temperature of the stars. The surface temperature of the sun is 570 5778 kelvins. This temperature corresponds to a peak emission equals to 502 Newton meter is equals to about 5000 angstrom. P is a constant of proportionality called Wheel's displacement constant and equals to 2.8977685 into 51 into 10 power minus 3 meter. In kelvins, 2.8977685 in 51 into 10 power 6 nanometer Kelvin. This is the Wien's displacement law of blackbody radiation. This is the Stephen Boltzmann law. J is equals to alpha T whole power 4, sigma T whole power 4. Gives the total energy being emitted at all wavelengths by the black body, which is in the area under the Planck's law curve. Explains the growth in the height of the curve as the temperature increases. Notice that this growth is very abrupt. Sigma is equals to 5.67 into 10 power minus 8 joules second inverse meter in square k power minus 4, known as the Stephen Boltzmann constant. These uh, these are the laws that are there in black body. Applications of black body. The area of Earth disk as viewed from space is area is equals to pi r square. The total energy incident on Earth is instant energy is equals to pi r square. Pi r square T S naught. The energy observed by the Earth atmosphere system as viewed from space is observed energy is equals to pi r square s naught 1 minus angstrom. As we know, the bodies must be radiative equilibrium. The solar energy striking Earth is As viewed from space, is re-emitted as thermal energy by the surface of the entire globe, as it is described by the Stephen Boltzmann law. Emitted energy is equal to 4 pi r square sigma t power 4. Set the observed energy is equal to the emitted energy. Solving the Ty's, we will get is equals temperature is equals to 255 Kelvin. As we see the right image reflected by atmospheric solar radiation shortwave, these are the applications of black body. Conclusion: as the temperature increases, the peak wavelength emitted by the black body decreases. As the temperature increases, the total energy emitted by increases because the total area under the curve increases. The curve gets infinitely close to the x-axis, but never touches it. The summary of this PPT is: a black body is a thermal theoretical object that absorbs 100% of the radiation that hits it. Therefore, it reflects no radiation and appears perfectly black. Roughly, we can say that the stars radiate like black body radiators. This is an important because it means that we can use the theory for black body radiators to infer things about stars. At particular temperature, the black body would emit the maximum amount of energy possible for the temperature. Black body radiation does not depend on the type of the object emitting it. Entire spectrum of black body radiation depends on only one parameter, that is temperature. Thank you. Thank you for giving this golden opportunity.